Yeah, it would be the biggest atom, but actually, is this recording? Yeah, it would be francium would be the biggest atom, but it wouldn't be very long-lived. So you have it, and then and then so the biggest the biggest stable atom would be cesium. Cesium would be pretty big. You know, rubidium was like 500 picometers in diameter. Cesium would be even bigger. Cesium is bigger because it has another shell on it.
So you said at 84 starts breaking up, right? 83
yeah, 83, like let's say 84 starts breaking up, right? Do you see that polonium? Bismuth. Did I talk about the polonium P thing? Yeah. Bismuth. Lead. You know, lead is the biggest atom that is pretty common. You know, lead. Although I have some bismuth, I need to make some crystals. Bismuth makes beautiful crystals. I don't know if you've seen it, but it looks like some futuristic cityscape, the bismuth crystals. And so lead is quite common, and so that's the biggest that's stable. So you want the biggest that's stable to absorb what? What do they use lead for? Yeah, they use lead bricks to block gamma radiation, and they use lead sheets to block X-rays. You need bricks because the gamma radiation is very penetrating. X-rays aren't as penetrating, so sheets are okay. Lead. That's for shielding. Why is lead? Why would you suspect lead is a good absorber of X-rays? This would be something that I'd test you on to see. I've repeated it so many times.
It's very dense.
It's not because it's very dense. It's related to it, but if it's very dense, then why not use? It's related. It's not because it's dense is the reason. Light is what? Light is electromagnetic radiation. So how does electromagnetic radiation get stopped by density? Because an atom, you got to realize, is an atom mostly empty space or mostly occupied space? And so the nucleus of a lead atom is quite dense because electrons don't weigh much, do they? And so is it because the tiny, tiny nucleus in the center blocks the X-rays? Or do you think most X-rays just pass through empty space? Do you guys remember the Rutherford gold scattering, gold foil experiment? What happened to most of the alpha particles? Went through, but gold is so dang dense, isn't it? Gold is incredibly dense, but all those alpha particles just shot through like it was nothing. And so it's not density the reason. And I know because I would think it's density as well. It's not density, it's because what do X-rays do when they interact with matter? Yeah, they excite electrons so much they ionize them. So lead has a lot of electrons to excite. The more electrons, the more the more allowed energies it absorbs. For example, hydrogen. Most of so the more electrons, you got to think. The more electrons, the more allowed transitions there are. The transitions will be the n equals whatever to n equals whatever, right? Those types of things. And so because it has a lot of electrons is the reason why. Otherwise, if it were just the density of the nucleus, then I wouldn't just suspect it do anything. Okay. And so that's a conceptual review for chapter 8. It's what does the radiation do to matter? In fact, speaking of that, you guys know what radiation does to matter, right? You reviewed it maybe several times. You reviewed it. Tell me what radiation does to matter.
Depending on the wavelength, it can ionize it.
Well, okay. Well, no, just go through the spectrum and tell me what each part of the spectrum does to matter.
Well, gamma and X-rays, they ionize matter.
Good.
Then UV break the bond.
Good.
And white light is
They
vibrate electron.
Yes, good.
Vibrate a little bit.
Vibrations, right?
Yes.
And radio wave is electron metal.
They,
Okay, microwave, we gotta do
they
microwave.
rotate the molecules.
Right. Microwave rotates the molecules, so.
And the radio, it excites the electrons in that.
Why would microwaves rotate the molecules? We'll come back to the earlier question. You know, because what do you think microwave ovens rotate? What molecule do you think microwave ovens? Water, right? Water. And so, what happens in water? The electrons in the bond are kind of tightly held, you know. And so microwaves just don't have enough push to excite the electrons in the bond, or actually and also, you guys remember this, delta minus and delta plus? Polar. Infrared is enough to excite the bond to get it to vibrate. Did I show you the vibrational modes of water? Yeah, so it gets it to vibrate. But microwaves aren't enough to get this, you know, these are too much inertia to get. And so instead of vibrating, it just rotates. So, you know, the electric field changes, plus, minus, and that flips the molecule. And so, you know what, I saw this video the other day, and so I didn't even know this was working here, actually, because I got an email, it was down, but let me show you this video. It's an ACS video, Chem Matters. And this is microwave radiation. I thought the audio was down, but the audio is working. So we'll watch this video here.
The year was 1946. World War II had just ended. The Raytheon Corporation needed to shift its efforts from fulfilling military contracts to the civilian front. They had already performed many experiments with magnetrons, radar tubes that generate microwave radiation. Excuse me. One day, Raytheon engineer Percy Spencer happened to walk by a row of these tubes while they were in operation. He also happened to have a bar of chocolate in his pocket. When he took it out, he noticed that it had melted. Curious, he placed some popcorn kernels near these tubes. He switched the magnetron on, and a few moments later, the popcorn popped. Whoa. Knowing that he was onto something, Spencer exposed a raw egg to these waves. It exploded and showered unsuspecting onlookers with egg on their faces. From these humble experiments, the idea of cooking food with microwaves was born.
Now, what are microwaves? A microwave is a form of electromagnetic radiation, such as visible light, X-rays, etc. It's just a form of energy that propagates in space at the speed of light in the form of an oscillating electromagnetic field. Now, what is an oscillating electromagnetic field? It's just a wave whose amplitude is changing over time. Now, why does water absorb microradiation? To answer that question, we have to look at the water molecule. One special thing about the water molecule is that oxygen is a more electronegative atom than hydrogen, which means that the electrons that form this covalent bond are not equally shared. They are pulled towards the side of the oxygen. That makes these covalent bonds polar covalent bonds, and they create a molecule in which the electrons are not evenly distributed. The oxygen that has a higher electron density is going to carry partial negative charge density, while the hydrogens are going to be left with a partial positive charge density. Let's look at what happens when we put a water molecule in an electric field. Let's say we create an electric field by having two electrodes, one with a negative charge and the other with a positive charge, that creates an electric field. If water is put inside this field, water will orient itself will point the oxygen with the negative charge density towards the positive side of the field, and the hydrogens with the positive charge density towards the negative side of the field. If water is exposed to a wave like this, water will have to orient itself according to the cycle of the wave. In microwaves, this oscillation happens about 2 billion times per second, which means that water molecule exposed to microwave radiation will force to orient itself many, many times per second. Here we have a very useful simulation that shows how microwave radiation interacts with water molecules. We can see that the oscillating electromagnetic field excites the rotation of the water molecules. Those water molecules collide with their neighbors and turn that rotational energy into translational energy or motion. And that is thermal energy, and we can see how the temperature of the system goes up. We're going to do a very simple demonstration to show that what heats up is the water input. We're going to place a piece of dry paper into the microwave and a piece of wet paper into the microwave. First, we need to measure the temperature of these samples, and we're going to use this infrared thermometer. So we measure the temperature of the dry paper. You can see is 74 degrees Fahrenheit. Now we're going to place it into the microwave for a few seconds. And we're going to measure its final temperature. As we can see, the temperature increased a few degrees because the paper traps some moisture from the air. And let's do the same experiment on the white piece of paper. We measure its initial temperature, which is 56 degrees Fahrenheit, and we're going to place it into the microwave for exactly the same time. When we measure the final temperature of the wet paper, we can see that the temperature raised up to 127 degrees Fahrenheit. That's because the water content of the wet paper is much higher than the water content of the dry paper.
The next time you reheat those leftovers in your microwave, we can't guarantee that you're going to get a great meal, but at least you'll know the physics and chemistry behind how your food is cooked.
Okay, you also have to watch out for ceramic plates. If there's a heavy metal glaze in the ceramic, like cobalt or some other, I shouldn't say heavy metal, but if there's like let's say transition metal, or there's some kind of metal in the glaze, let's say if there were lead in the glaze, you know what would happen? It gets extremely hot. You wouldn't want to even touch it. Why? If you had, let's say, a lead glaze on your, or you put lead crystal in your, if you put lead crystal in your microwave oven, it's going to get blazing hot. Foil will cause some excitement there, but it's the same reason. Why? Yeah, metals have easily excitable electrons. So let's say lead in the glaze. Although metals don't make good microwave antennas, microwave generators. You need these things called tunable. The wavelength of a microwave is about 9 to 10 centimeters, 2.4 gigahertz. I think it's like around 9.5 centimeters. And you create a staining wave in your microwave oven, with a wavelength about like that. And so you can tell they're going to be hot spots, something like that.
Have you seen someone put a grape in a microwave and raise plasma?
No.
It's weird. Like they get a grape and they kind of half put it in a microwave and starts generating plasma.
Yeah. Well, microwaves are used to generate plasmas all the time. I generate plasmas using microwaves. It's very common, but usually generating microwave plasmas at room pressure is very difficult. I did it under vacuum conditions, and then it's quite easy, except to initiate the plasma is hard. And so to initiate it, you give it a little spark using a Tesla. I don't know. I don't know what's going on with the grape, but I'll take a look at that.
Yeah.
Well, anyway, that's So
How do you call the diagram where you have like 1, 1?
There's
Like where you have like where your name is the principal shell, the subshell, the...
Is it the orbital?
How do you call that?
Energy level.
Oh, it's energy.
No, we actually like that. You have one over
Which diagram is that?
Is it the orbital energy jet?
Instead of calling it like one answer, we call
Just
it
remember in
one.
the solution,
What you're
showing
talking-
the
What you're thinking I'm naming is the electron configuration.
Electron configuration.
What I'm naming is what you're talking about, which is the energy level.
I think what you're talking about, you know, if you're talking about the 100, there's no diagram. That's just just a different way to name the orbital. And so, you know, you don't have to have a specific diagram to go 100. You know, that's just NLM.
Yeah. I was just wondering, like, if you wanted us, like, I don't know, you got to develop a test or you want to just name that. Like, you know, as a time.
Yes. Right.
It's the orbital energy diagram, right?
Orbital energy level diagram, you need to know how to label the orbitals. If I have a bunch of orbitals here, like for example, this is the lowest energy orbital, what is it? But it's not just 1s, it's also called psi 100, also called a
100.
100 orbital. Get rid of the psi.
So that's what
Make
I'm
it-
saying, like, how do we know when to use the psi equation or when to use the...
That's the same.
They're the same, but you know what? I ask you, what did you look at that practice exam?
You didn't have any. We're going to do this.
I didn't have that on the practice test. Practice test 10. Basically, let me just make it quick. I ask you to do both. Label it using the
You said one electron species, and then you said,
right. But the thing is, okay. If I ask you to draw this diagram, are you going to show? If you know this information, are you going to hide it? Because I don't know if you know it or not. But just as a basic philosophy, if I ask you to draw an energy level diagram, would you try to write, you know, as much stuff as you can? Yeah. And so what I was expecting with the energy level diagram, you don't have to do this because psi 100 and 100 are the same, but something like this would show me that, wow, you know both. Whereas if you just drew this, then I think, oh, maybe you don't know.
You don't have to put that side one, you can just put one on.
Show off.
Or you could do this.
Just to show up the numbers. Yeah. The bottom show.
Can you still,
I'm not clear yet.
How high you have to go? How high you have to go? What did I say? How high you have to go? Does anybody remember? You have to complete the fourth, not the fourth level. We call it the fourth shelf. Typically, if you say fourth level, you're talking just n equals 4. You know, there was a question on Piazza. The principal level, it's the principal energy level, which is n, the n level. And so the fourth shell, and it has to be complete, unlike the book. And then when we did the example, I said, you got to be able to know each, if I pick this orbital, what are the quantum numbers, right? If I pick this orbital, what are the quantum, that means you have to know the quantum numbers for all of them, okay? And if I ask you to draw it, then you should label it with both then. You know, yeah, you should label it with both.
Like separate or the same?
No, you could do it, what do you mean separate or the same? No, not separate, the same, on the same diagram, you can label it both. On tests, it depends, you know, on tests sometimes I'll say, you know, label it with both, the quantum numbers and the NL, you know, letter, number combinations.
can you show an excited state and then ground state in the orbital energy level diagram? It's like the difference, like side by side comparison.
Okay, this would be ground state, and
This would be like, say, an excited state here.
Oh, okay. Because in the book it has like multiple like energy levels.
Let's take a look at the book.
Yeah, I think it
This
was
is
like
working. So I can
80.
show this thing. This small.
It's like page 80, page 356 and then like number 84.
So take a look at that specifically. Is there another question while we wait for this to come up?
And the practice exam number 9, I don't get number 14. Like, I don't know if there's some information that...
I think I got it. Like I haven't even started, but I think I got it.
I don't know if there's any information that maybe you wrote before when you gave this exam.
Oh, this is that one where you like that.
Just read the question out to me.
We just determined the standard enthalpy information for nitrogen monoxide.
Oh, we have to go that way.
But then when we did the example in class, we had the different equations and then we had the final equation
All right, let's take a look at it.
as a reference.
I'll take a look at it. We'll go to this one first. What page was it? 384?
356.
356?
Yeah, 356.
What number?
84.
84.
So like C would be like excited, but
They're all excited.
What neutral atom do the following valence shell configurations correspond? Indicate whether the configuration corresponds to the ground state or excited state. A.
It is excited.
Yeah, this violates what?
It violates the rule that there has to be one electron per.
Hund's rule. Violate Hund's rule. This is which one? Would be, if this is a valence shell, this should be, if it's neutral, it's a thing neutral, the neutral atom. It's not an ion. This would be what element? Silicon. Yeah, we just looked at it. Yes. All right, that's excited state. What is this? This is excited because you see that this would be a violation of Hund's rule. This would be phosphorus. This is ground state. This would be sulfur. Sulfur wants 2 more electrons here. So ground state doesn't violate anything.
Because it doesn't violate anything?
Right.
Oh, so it's only excited if it's violating something?
Right.
Oh, okay.
The rules are for the ground state electron configuration.
Oh, okay.
Professor, why is it B exhausted?
Why B? Because Hund's rule says parallel spins. This one's anti-parallel.
Okay.
Professor, do we have to know the rules by name or do we just have to know the concept? What?
You should know the rules by name. There are only 3 names, right? Offbound, Hund's, and Pauli. Because I'm going to ask a question like, this violates which of the rules? What are you gonna say? Rule number 1, rule number 2, or rule number 3?
Well, I would say election.
It violates one of the rules, but what specifically?
Election has to be parallel.
That's too much writing. Sorry. D, that's excited state of sulfur, where the spin's been flipped. All right, what was your question about then?
Go ahead. See?
What was the information that was given?
Well, you have the.
NO. I gave you 3 equations?
Yeah.
Then we have to have the final equation to use as a reference.
No, because you should know the definition of formation. Did I ask you?
And then we also have the values for delta H.
Here, let me take a look at that then.
Piazza, the online
Okay.
Q&A platform is incredibly easy.
I didn't check it this morning. It was at
Sam number 9.
exam 9.
Question 14.
Yeah, I didn't give you the final equation because you should know the definition of a formation reaction. NO. And so I tell you it's a formation reaction, which means that what is the definition of a formation reaction? No, that's not what I want to hear.
One more.
It's the, yes, that's what I want to hear. It's the,
One more. One more.
no, yeah, formation of,
One more. Pure elements. Yeah, pure element and one constant.
yeah. I don't know, that sounds shaky for having reviewed it many, many times by now, right? It should be a lot more automatic,
This one is
you know?
more stable.
Because if I ask you what is the definition of formation, it should be automatic. Formation, yeah, that's right. I mean, those are good. But it should be, it should be quicker. And sometimes, what's even better is if you put it in your words, which you are doing, but your words don't sound like, they're coming, if you put it in your words and they're well thought out, then it's going to stick. If you memorize somebody else's words, well, it's okay, but it doesn't stick as well, right? And so the pure elements, that's good, yeah, in there. And under the, what conditions?
No one more.
Well, under the conditions given, whatever they are. And so you should know the definition of this. What I'm asking you is it under standard? Standard enthalpy of formation of NO. If you did you look at Appendix D?
Yeah.
Do they give you any of the reactions? Delta H is for reaction. Did they give you the reaction itself? No, because they expect you to know it. What is this delta H for? They give you this delta H value in Appendix D. It's something, something, something kilojoules per mole. You look up this number. All they give you is this and the number. And so what is that delta H? It's for change. Delta H is a change. H final minus H initial. But what is that change? What is giving this energy? This is actually exothermic. What is giving that energy? Exactly.
Heat reactants minus heat.
Not the heat. If you're talking about the heat of the reactants minus heat, that's like temperature change. The temperature change is this heat exchange, right? No, it's not that. This is a process. What is the process? See, this type of stuff I don't really, because this type of stuff is more straightforward. It's just you read it in the book and then you go, okay, that's it. But you should know it. I didn't spend a lot of time talking about it because I thought, you know. And so what is the reaction? Well, the reaction is a formation reaction. This much energy released when, what exactly happens? When 1 mole of NO, and we need to know the state, it's gas. When 1 mole of NO gas is formed from?
1 mole NO liquid?
No.
N2 plus N2.
Yeah. Boy, I'd love to postpone the exam, but unfortunately we can't because it sounds like you guys aren't ready for it. Quite ready for it. Remember the thermal. What did I say about the thermal? The thermal is hard because it's got all that stuff you got to keep track of. And to try to cram that, well, I don't know because I'm just getting, maybe you have it all down. But to remember all those things takes time. If you tried to cram it overnight, one night, then you're going to join the club, you know, of what most people do.
So what we do then is we write the equation of formation like you said, and then we just do the same.
Right. You do the same thing.
The reason why I got confused is because the example we did in class, we didn't do that. So
I know.
The final equation was given to us. So
Right.
I was expecting.
No, don't expect. I mean, this is just an added twist. It's like this is kill 2 birds with 1 stone. That is, can you do Hess's law, and do you know what a formation reaction is? Do you think? And so sometimes I'll do that. I'll just have 1 extra step, and having that 1 extra step stops people. You know, it gives people trouble. This is why I get a lot of blank, because if it's just like, even if it's just like what I did in class, that sometimes stops people. But in this case, I throw in 1 extra step where they have to do this, and it's difficult because they don't know it well enough to make a connection. You know, to connect what we have to do. And so your question is very common during the test. A lot of people came up to me and said, well, what is the reaction we're trying to solve for? Lots of people came up to me during the test, asked just that. But anyway, it's a standard enthalpy. Determine the standard enthalpy of formation of NO gas. So we know the standard enthalpy of formation is this. This is how much energy is released when this reaction occurs, as written. And this is appendix D, so the starting temperature is 290, and the ending temperature is 290. There's no change in temperature. It's a process, it's a reaction.
Then we also need the values of delta.
We don't need the values of delta because I just want this. I didn't want you to punch the calculator. I just want you to go like we did in class. Yeah, delta H of formation is equal to 1/2 delta H1 times something like that. That's the way I wanted it.
And the last one, instead of being delta H1, it would be delta H3, right?
Yeah, this should be delta H3. That's a typo. But let's take a look. Is this first reaction a formation reaction?
Yes.
Yeah. The first one. So I could have made this more difficult. I could have just said, I'm not going to even write this equation down. I'm just going to tell you the delta H of formation is ammonia. And then you have to write down the equation, right? Is this a formation reaction here? No. And so I would have had to write this one down, the complete equation. This last one, is this a delta H of formation? Yes. And so this one I could have just said, determine the standard enthalpy of formation for NO gas, given the delta H of formation of this, and the delta H of formation of this, and then I write the equation. And you know the question I get asked? The question I get asked is, oh, we don't have the delta H of formation of this. Because I need to take the delta H of formations of the products minus the delta H's of formation of the reactants. Something like that. And what is the equation? And so, it brings up a lot of confusion. And so this is just one of those things where in thermo, there's so many of these definitions that you have to keep track of that it makes it very difficult. And so the easiest thing to do is just to, This is pretty much, you know, you start off on the ground floor and then just work your way up. Because, let's see. This is not.
Can you just show us how to do that problem?
Yeah, this fractions are like.
Well, that makes sense, I just don't know what after, like.
You know, this isn't even all of it, you know, but you already know internal energy, right? You know Helmholtz free energy? You know enthalpy, right? You don't know Gibbs free energy, but Gibbs free energy is covered in Chem 1B, but there are actually a lot more. This isn't very thorough. This is Wikipedia. All right. And so all of a sudden, you know, the next class, let's say, if you're interested in, like, say, even if you're a biology major, did I tell you they have thermodynamics for biologists? Yeah. Because energy is important for biological systems.
Like,
Right, and so, of course, engineers, right? And so the next class you're going to take after this is a proper thermodynamics class. And so if you don't have this stuff down, then you're really, again, you want to, don't put yourself at a big disadvantage. But anyway, you want to do this problem? You can do this problem. How many people got this problem?
I got confused by the way it was explained here.
Well, I know that everybody's busy, so. If you have plenty of time, then, you know, all the classes would be a lot easier. You're juggling a bunch of stuff. But this is why I like to study from the notes, because I can do that every day, and and it's quick, you know, for me, and it's complete. So, again, by this time, I would have gone through this delta H formation so many times. So it would help. Well, anyway, this is the equation we want. We want 1/2 N2 plus 1/2 O2 yield NO. These are all gases, so I'm not going to deal with writing the gaseous state. And so all we want is, we want 1/2 N2. If you look at reaction 1, you're going to call this 3. Yeah, this is a typo. Reaction 1, we have 1/2 N2, so I don't have to do anything there. So what I'm going to do is I'm just going to use reaction 1, 1/2 N2. Actually, I don't. They aren't all gases. I got to write my state. So 1/2 N2 plus 3/2 H2 yields NH3. Actually, what I'll do is if it's a gas, I'm going to leave it off. And so we got delta H1. This is under standard conditions.
Yeah.
Okay, what do we need next?
The second one cancels out.
No, just turn by the 3 over 2 for the third one.
We need the third one?
Yeah.
All right.
My 3 minus 2 cancel everything.
Okay, times
3 minus 2. 3 over 2.
3.
Minus 3 over 2.
Okay.
You cancel the water, cancel everything.
Well, here we got N2, hydrogen, and ammonia. So this is my strategy. I have a 1/2 N2. I want a 1/2 O2 next. And so 1/2 O2 you could get from the from the second equation or from the third equation. And so 1/2 O2, you know what? I'm just going to take the third equation. Use it as is?
Yeah, do the third equation.
Use the third equation as is? All right. Well, it seems, I mean, I got a half O2 there, might as well just go ahead and use it. H2 plus 1 half O2 yield H2O. This is delta H3.
Yeah.
Okay, now I need 1 NO. And I got 1 NO right there in the second equation. So let's just go ahead and use the second equation as is. NH3 plus 5/4 O2 yields NO plus 3/2 H2O liquid.
Because we tell -3 over 2 over third equation, we cancel everything.
Oh, is it?
Yeah, this time 3 minus 3 over 2 for the third equation.
3 over 2 for the third equation?
Yeah, minus 3 over 2 we inverse.
Yeah, should be reversed.
Yeah, we reverse.
Cancel out the.
Well, then we can cancel the.
Yeah, you're right. We need to cancel out the hydrogen.
Yeah, that's right.
Yeah. But after we do that, then where are we going to get the NO?
We plus the second one, we can cancel.
Okay. So we shouldn't have used this one.
No. Wait.
We should use that.
I mean,
we're gonna flip the.
we should flip it, you're saying?
And make it.
We time it minus 3 over 2.
Times 3 over 2, okay. So 3/2 water plus
Plus 3 over 2
Yield.
hydrogen.
3/2 hydrogen plus
And 3 over 4 oxygen.
3/4 oxygen.
And now we plus the what
So
the
this
first
would be
one
minus 3/2 delta H2.
3.
Delta H3.
Well, no.
3.
Yeah.
Yeah, and then we plus 1 in the third.
And then boom, everything works out.
Then boom, everything works out?
Yeah.
All right.
It's half oxygen.
All right, so then this means that delta H of formation for this is equal to delta H1, what do we do? Times delta H2 plus delta H2
Minus.
plus a minus 3/2 delta H3. Okay, and just make sure everything cancels out. Ammonia cancels out.
Yeah.
The hydrogens cancel out. That's good.
3/2 H2.
Yeah, this cancels out. And 3/2. And then we're good. Yeah, you're right. That was the best way to do that. All right, so this is a Hess's law type problem. Hess's law, like I said, Hess's law aren't difficult as long as you have enough time. Because if you get stuck, you just backtrack and try a different thing. That's all you do. Fractions make it tough, yeah. Fractions are going to make it a pain.
So that's going to be able to.
Boy, I'm glad you guys are figuring out what's going to be on the test. It should be pretty obvious what's going to be on the test, right? The stuff I cover in lecture, right? This is why I say, if you can't do the problems I do in lecture, right, those are the first problems. And I can't believe, like that, this is why I was so shocked, because I've been telling you this, right? And then we have the successive approximations, and you haven't even tried it night before the test? That's a little bit shocking to me, because I tell you to first make sure you could do. Remember, I said something about the piano way at the beginning of the semester. I said, can you play the piano by watching somebody? Okay, the concert is like the test. So you're going to go to the concert. I've been watching this person play the piano, say Mozart or something. I've been watching, carefully studying it, right? And then the next day you're going to go play the piano? No, you're going to find out, wow, it's a little bit more difficult than I thought. Well, the same thing with the problems. We do them on the board, right? But are you just going to watch and say, okay, or maybe, it's also okay to do this. That's too hard. It's going to spend too much time thinking about it. I'm just going to hope it doesn't appear on the test. And, it depends on the test. It's okay for my style of test, but not for UC style of test, because UC style of test, they're going to ask you maybe 4 questions. That's 25% right there you've lost if you decide to skip it. But for my style, maybe it's 10% you lost, And so it depends on how much time. It's always, I know you guys are pressed for time. It's always the time versus benefit. This is why when I say, at the beginning, of course I want you to know everything in this, this is close to 1,000 pages. Well, actually, let's divide it in half. 500 pages. I want you to know everything in those 500 pages, but is it a real, could you do that? No, it's too much. You know how much stuff we skipped in chapter 8? A lot. You know why? Because we just don't have time to get into that much depth. You want to sit there and read and study from the chapter? Reread, do all the calculations, polar coordinates, plot. Is that, to me, that's a waste. You're wasting time. You're wasting time because you aren't focusing on what the most important stuff is. And it's so obvious what the most important. Did I do one of these Hess's Law in class?
Yes.
Do you think I'm going to waste my time doing that if I'm not even going to ask you on the test? No! I hope that was sarcastic. I know that's kind of been sarcastic. Is it going to be on the test? Yeah. That's a joke.
Question.
Yeah.
As far as the memorization goes for the pages, like for chapter 8, like there are a bunch of expressions. Like, are they supposed to all, like,
No. For chapter 8, none. None. Chapter 6, none. But chapter 7, I don't want to overload you with equations, but chapter 7 you have to memorize those, because if you don't have those memorized and you just know the equation, like a lot of people know this equation, delta H is equal to delta H of formation of the products, minus the reactants. But what are the restrictions on that? And so this is why I want you to memorize the equations in chapter 7. Well, the temperature has to be the temperature of your given data, and the pressure has to be 1 bar, right? All that type of stuff. There's so much additional stuff that you have to memorize.
What about chapter 8?
Chapter 8, no. I'll give you all the equations in chapter 8 and all the constants.
Even for the speed of light, like C.
Even for the speed of light, yeah. I don't expect you to memorize the speed of light. The reason I'm going to give you all chapter 6 and all chapter 8 is because those are a lot easier to memorize than the chapter 7 ones. Chapter 7 is hard, so I don't want to overload you with stuff to memorize. I'll tell you though, if you take a standardized test, let's say you take any kind of standardized test, they don't give you any equations. You have to know it. What?
For that one, can we not use one like with so many fractions just for time? I'm concerned about it.
No.
Can we just get a cost for it?
I wouldn't worry about it. Save it for last, and then see. Yeah.
How many equation of formation don't we have to remember?
How many delta H's of formation?
I mean the reaction formation, like NO gas.
How many equations do you have to remember?
I mean, not equation, reaction we have to remember.
How many reactions?
Yeah,
delta H of formation?
Yeah. All the more we don't remember the nitrogen origin from the NO. Yeah, that's true.
How many do you have to remember?
Yeah.
Okay, you could either remember the pattern or you just memorize all of them. All infinite of them. It's not really infinite, but it seems like an infinite number.
What about appendix D?
Appendix D? I think they're asking about that delta H of, you have to know the delta H of the equation.
Yeah.
How many equations do you have to remember? For chapter 7?
No, not
Just like the equations, like to come up with, like for that, how you determine that equation, like how many of those, or like which ones would be significant to remember?
You should just know it.
Or like
the mole of whatever comes from.
And we know that's an NO gas.
You should know the pattern.
Okay, let me still here.
Yeah, but some of them like NH3 plus O2 plus nitrate.
We know that NO down goes.
Let me make sure it's clear, because I'm not exactly understanding, actually, I think I'm understanding your question, but,
Like those equations won't be given to us in the test.
which equation?
Like, you know how we came up with N2 plus N2 equals yields to, like,
This one, N2 plus O2 yields NO?
yeah.
We know.
How many of those do you have to know? Well, let me count for you. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16.
We get
This is complicated.
we get the
Let me go on.
So I think it seems.
Okay, almost done, almost done. Almost done. All right, 587, 599. Okay, that's how many you have to know. I'm sorry, because, I don't understand why it's so difficult. It's so easy. Let's go to methanol. Delta H of formation is minus 200.7 kilojoules. And wait till you see how easy it is. I can do, you know what, I can do way more than that. I can probably do 10,000, 20,000 of them in my, but you don't need any specialized memorization technique. You just have to know what the elements are. That's it. And so if I do methanol, it's formation of, and so this is the delta H of reaction of what? Delta H of reaction, under standard conditions, is equal to delta H of formation because it's a special reaction. This is methanol liquid. What is it? Well, it is minus, actually I'm going to go, methanol is normally a liquid at room temperature, so it's minus 238.7 kilojoules. Minus 238.7 kilojoules. Okay. So what is the reaction? Yeah. C plus H2 plus O2. That's it. And then we got to balance it. One carbon, 2 hydrogens I'll need, and half an O2. And I'm done.
so it's just the elements are.
Pick any of those. There are probably 600 of them. Pick any of them.
Plus H2.
I'll do it for you.
So
Which one do you want to do?
The last one.
Let's do something, let's pick the most complicated looking one.
UF6.
Ooh.
That one, sodium.
How about this one? Sodium
Yeah.
sulfate,
Yeah.
decahydrate, solid. I'm gonna do that. I wish every test were this easy, you know? Yeah, when I was a student, I'd wish every test was this easy, because once you know it, you could do any of them. It's so easy.
sodium.
Delta H of formation is equal to minus 4,327 kilojoules. All right, let's do it.
It's sodium.
2 sodium solids plus sulfur plus oxygen. How many oxygens do I need? 7 O2s plus 20 hydrogens, so I need 10 H2. H2 is a gas, O2 is a gas, sulfur is a solid. I'm done.
Does it need to be kilojoule per mole or just kilojoule?
No, this is kilojoules per mole of product per 2 moles of sodium, per 1 mole of sulfur, per 7 moles of O2, per 10 moles of hydrogen. It's kilojoules for the reaction as written.
Well, I would say scroll up, you get the tab, and it says like kilojoule per mole.
Yes, it would be kilojoules per mole of only this, but you don't have to write that. There's two ways of writing this. It's kilojoules for the reaction as written, or kilojoules per mole. If you did per mole, then you have to specify. It's not, could this be right? Is it per mole of hydrogen? That's wrong. Then you have to specify what it is. Well, it's Na2SO4 sodium sulfate dot penhydrate.
Professor?
Yeah.
So if we didn't know that value, you would give us the 3 questions, right?
No.
And then to manipulate this information?
No, I'm not. Every question is not going to be about figuring this out. You know, some questions are going to be just, you know, which is the correct. Did you look at the multiple choice? I guess you haven't looked at it. What was the type of question I asked you about delta H of formation in the multiple choice? Andrew knows which one I'm talking about. Which one? The one where you asked me, this isn't it because it's for 2 moles. Remember that? You said this one's 2 moles. So you were asking me to check it. Maybe it wasn't you. Maybe it was somebody else. Then somebody else was asking me. Somebody else is asking me about. Actually, it was on the practice test. So I mean, we should just review this. Anyway, did you look at the problems in the homework? What kind of problems did you have with delta H's of formation? You know, if you looked at the homework, then it should be pretty obvious what types of questions, the typical questions. And then after you've gone through all those typical questions, then I might throw in an extra twist. That's exactly what I did with that one problem. I said, you've already gone through that. You've gone through all the delta H's of formation problems. You've gone through all the Hess's law problems. So you just put it together into one problem. You know? And so when I was looking at that, I'll show you in chapter 7. So, you know, I only assigned, I think, one of these, but there are a whole bunch. If you want more fractions, look, number 67, fraction. Actually, look at number 67 carefully. Here, the standard entropy of formation of ammonia is minus 46.11 kilojoules per mole of ammonia. You see the, say, per mole of ammonia. Actually, this is per 2/3. And so we got to be careful because this is not the delta H for the reaction it's written. If they just gave us the delta H, then it would be for 2/3 mole, not per mole. Do you see? Sometimes there's no 1 as a coefficient. Sometimes we have like 2, 5, 8, 9, 3, but no 1s. And in that case, we do it for the reaction as written or per mole. But if it's per mole, then there's a confusion because the reaction is written differently.
So for this one, do 2/3 and then kilojoule value and then switch the sign?
Yeah. Yeah, this is for 2/3, so yeah, it'd be 2/3 of that, and rather than being exothermic, it'd be endothermic here. But look at 68 fraction, 69 fraction, 70 fraction, 71 fraction, 72 fraction. You know, all these are fractions except for 74, 75. And so the one I assigned is a fraction because I thought, okay, you might as well get some practice doing fractions. I think I only assigned 1 or 2, right?
Just 1.
Yeah.
Just 1, because 1's all you need.
No, actually 2.
Yeah,
2, okay. All right, then we had some other stuff.
Have you do problem 64?
I'm sorry?
Chapter 7, you do problem 64.
64?
Yeah, drawing the diagram show delta H and less than or greater than delta U.
Okay. Let me finish my little spiel about the standard entropy of formation. Okay, so here we have our problems with standard enthalpies of formation. And if you look at these, all right, we're going to use the standard enthalpies of formation to calculate. So this is just delta H is the product minus the reaction. Standard enthalpies. Same thing here. Same thing here. Same thing here.
So for that, we use a table, right?
Yeah.
So you will give us
Appendix D, right?
You will give us the value.
Yeah. Except, what is this? Use standard number in table 7.2. Use data in figure 7-18. Use appendix D.
So does that
Yeah. Use this. Use standard, data from table 7.2 to determine the standard heat of combustion. You know what a heat of they didn't tell you what the reaction is. What is the reaction? You see, here we're given the equation, given the equation, given the equation. All of a sudden, you are given the equation. What do you do? Well, you have it memorized. You know what a combustion reaction is. You just write out the combustion reaction and then figure out what the delta H is. So there's twists, but these twists are more apparent when you look at a lot of problems. If I only assign one problem in the whole set, then you don't necessarily see it sometimes. And so this is the advantage. You have the solutions guide. You can just look. But this is a standard. This is, all these are so standard. I don't want to assign that many because it's just repetition, and you don't need that much repetition, I think. Appendix D, Appendix D, Appendix D. So let's see if there's another one with a twist in there, or are they all this straightforward? And so we go to 91. Oh, this is a little bit of a twist. They don't give us the equation, but they give us the reactant and products, and they make us balance the equation and then use the appendix D data. This is another twist, right? Because here, the volume of butane measured that must be burned to liberate this. And so this twist is not only do we have to figure out what the delta H of combustion is from the appendix D data, then we have to do a stoichiometry calculation and a gas law calculation to figure out how many liters of butane are required to do this. And then we go ants release this formic acid when they bite, use table 7.2 in the standard enthalpy of combustion. Ooh, look at standard enthalpy of combustion for formic acid to calculate the standard enthalpy of formation for formic. This is a double twist, right? This is a double twist because ants release, we want the standard enthalpy of combustion for formic acid to calculate the standard enthalpy of formation for formic acid. And so this is even harder than the one I gave on the test because you got to know two definitions. You got to know one, you got to know the definition for standard enthalpy of combustion and what that equation is, and then you got to know what is the equation for standard enthalpy of formation so you can add up the equations to get the right equation. Here, that's number 93. Number 94, calculate the enthalpy of combustion for lactic acid by using the data in table 7.2 and the standard, well, this is a repeat of kind of this, so once you've done it once, this one's not so hard, do it. But that's it. So we've gone through the whole section, and most of them are straightforward. So most people can do the straightforward one, right? And then you throw in a little twist like that, and I end up getting blank page, blank page, blank page. And people get stuck. I'll do it, but I'll tell you, UC gets worse because, if they gave you a problem like the homework, then that's a gift. You consider it a gift because you've gone through all the homework problems and you know. They're going to throw on another twist on top of any kind of twist they throw in the homework, right? But you're going to be prepared for that because you've gone through this. And so if they throw in another twist trying to relate it to something else, then you go, oh, okay, I got that. You know, I could figure it out. Okay. But if you're just struggling with the basic, then you're never going to get those problems, which is okay. I mean, not everybody has to get those problems, but you don't want to miss too many points, though. It's possible. Yeah, there's another difference between, like I said, like 4 questions. The other difference is the average. You know, the average on the test that I took at the UC were very low. Very low. But the problem is because they threw on some very hard problems on there that they didn't expect people to finish. They said this problem is going to be too hard to finish. And what they're looking for is they're looking for, you know, they have thousands of students. And so, you know, thousands of students come by and then all of a sudden one person gets that problem. You know, and then they go, oh, that person's special. And so this is why they want to put this, you know, one super challenge problem often on test to see, okay, the outlier, they call it, or something, you know. And so a lot of times you don't finish the test at all, you know, a lot of exams. You don't finish and there's not enough time to go back and check the answer. But the better you're prepared for this by just nailing, you know, it's just getting the basics down. The thermal is just getting the basics down, you know, and just repetition and then just grinding it into your brain so that it becomes more automatic. Then better. Well, these, you know, this is one of the reasons I like Petrucci, because he has the integrated and advanced exercises, and these throw on an extra twist. So what we just saw there was the basics, and then we'll look at, you know, what else can we do with Hess's law over here. And over here, I don't think I assigned any Hess's law problems, did I? No, I didn't. Were there any Hess's law problems over here? No, let's take a look. You know, what we do is we just try to, the scientists are good at observing, right? And so we use like observations. Okay, unit conversion, BTU, you know, and to calorie, specific heat, okay. This is just, you know, hot metal cooling down. This is bomb calorimetry. This is bomb calorimetry. Combustion of hydrogen, liquid versus gas. This is why I say, you know, what's the water going to be? When you combust it, a lot of people say when we combust methane, the water should be, or combust hydrogen, the water should be gas. But that's not the way we work in thermodynamics. This is a question, this would have been a twist on the question I did earlier. In processes, let's see if you nailed this down. In processes, what happens to the kinetic energy in going from the initial state to the final state? What happens to the kinetic energy in going from the initial state to the final state in a chemical process or reaction? Nothing, right? That's good. Okay, you got it. And so this is the same thing. If the water goes to a gas, then not only do we have a change in potential energy, but we also had a change in kinetic energy. We can deal with that, the calculations to deal with that, but we don't want to deal with it at the same time. And so usually if you're given a problem like that, you break it up into 2 steps. One is the potential energy, and that would just be Q is equal to the amount times delta H or delta U, and then you do a Q is equal to MC delta T to warm up the water into water at 100 degrees C, and then you do a Q is equal to the amount times delta H to vaporize that water to get a H2O gas. It depends on what the temperature is, the final temperature. The other thing is, you could do H2O gas at 25 degrees C, you know, because H2O gas does exist at 25 degrees C too. Vapor pressure of water. But anyway, there's a difference in energies here, and so this is kind of looking at that, why we do that. And so this, you know what this is? this is Hess's law with an additional twist. How many people would have been thrown off by this Hess's law problem? Just a second. Let me get to your question. How many people would have been thrown off by this? Determine the missing. Whoa, we got 2 missing values. Well, we really don't, because you should automatically see one of these missing values is going to be super easy. Which one is it? The left one or the right one? The right one's going to be super easy. Why? Because you should automatically recognize this reaction. What is it? This is 2 times delta H of formation of NO2 gas. 2 times, because we're forming NO2 from the elements, but rather than forming 1 mole, we're forming 2 moles. So we just look up in appendix D, delta H formation of NO2 and double it. That's this, and then we can get that. Super easy problem, right? But how many people would not get it? A lot. A lot. Because it looks different. It's not what I was expecting, right? It just looks different. But the more, the more variation you see, the less surprises. And how do you see a lot of variation? Well, I told you about the pre-meds. My pre-med friend, right? My pre-med friend looked at every single problem in the book. And then I thought, why are you doing that? The instructor didn't even assign a fraction of those, right? In fact, no homework was even collected in that class. Why are you doing every single problem? Well, pre-med, that's why. Pre-med. Pre-med is kind of, some people get very intense pre-med because they're, it's like that thing. There are very few spots in medical school and lots of people want to get in. It's very competitive. I didn't like, I wasn't into that scene, the pre-med scene. So there are a lot of people, you'll notice, a lot of people who are regular, just kind of science people will disparage pre-med people because they make the class hyper-competitive. And if you're pre-med, then, that's great. I admire your, but for me, a particular natural gas consists in mole percent. So, this is a mixture, but it's a 3-component mixture. But the nice thing is they give us the components here. And so this is just a chapter 6, a gas mixture. When you see the percents here, mole percent means the same thing as volume percent, which means the same thing as pressure percent. So probably the easiest is just to do the volume. We calculate the volume. 385 liters, 83% of that is methane. So we figure out how many liters of methane, we can figure out how much heat, right? And so this is some chapter 6 stuff thrown in there. Show this overall can be an appropriate combination of equations from 7-9. I don't want to go back there. But, you can see different twists on things when you look at all these, A lot of calorimetry. Somebody asked me, is calorimetry going to be on the test? Yeah, I can't leave off calorimetry because a lot of questions include calorimetry as a start, and then you have to do more work on top of calorimetry. It's like one of those parts. And so even though you were tested on calorimetry, you were just tested on calorimetry alone. This is going to be calorimetry plus a twist kind of thing, right? Like this, these kind of things here. And so, well, anyway, let's go back. I don't want to, I spent too much time, sorry. But you had some questions. What were the questions? What did you want, 64?
Yeah. And number 18 for exam 10.
Okay. So let's look at number 64, then number 18. 64, determine whether delta H is equal to, greater than, or less than delta U for the following reactions. Keep in mind that greater than means more positive. Do I want you to keep in mind that greater than means more positive? No. I want you to ignore that completely. And so for number 64, energy is always positive, so we'll just take the absolute value of the energy, and that'll tell us which one is greater. More negative. Assume that the only significant change in volume during a reaction at constant pressure is associated with changes in the amount of the gas. And so let's say if there are a liquid over here and you have a new liquid over here, we're going to assume that the densities of the two liquids are about the same. Or if you have a solid over here and a solid over here, density is about the same. Or if it goes from a solid to a liquid, close enough. It should be different, but close enough. So the complete combustion of 1 mole of butanol, 1 butanol. Did you write out the equation? Well, just tell me what the equation is. C4H9OH liquid.
No, not OH, C4H9O.
C4H9O?
Yeah.
It's butanol.
That's really C4H8.
Well, actually, let's just do CH3, CH2, CH2, CH2OH. And so 3, 5, 7, 9. Yeah, and then it's got to be that.
What?
Plus 3O2.
Here, how many hydrogens?
3.
Plus 2 is 5, plus 2 is 7, plus 2 is 9, plus 1 is 10. You could write it C4H10O. That's okay. But people don't usually write this because do you know what isomers are?
Yeah, they're different.
Isomers are the same formula but different structure. Now, if you have an O here, it isn't necessarily an alcohol. You know, it could be what we call an ether or some other organic functional group. Liquid plus 3O2 gas yields
CO2.
how many CO2? 1? It can't be 1 CO2. There are 4 carbons.
It's 4 1.
4 CO2s? But this, somebody, the O2 seems a little small, but we'll check it. Plus how many waters? Plus 4 waters? It can't be 4 waters because we have 10 hydrogens, so it's going to... So the first part is you got to get the equation right, and so let's make sure it's right. This is going to give us 8 plus 5 is 13 oxygens, right?
13.
The oxygen is 1.
Yes.
602, yeah.
602.
602, 4 carbon.
Alright.
That's good.
Combustion, exothermic or endothermic?
That'll be excellent.
Exothermic, so delta H is less than 0. It's combustion. What's happening with the volume?
Volume is increased.
So here, which one do you guys like? Do you guys like to do the H enthalpy diagram or the U internal energy diagram? What did I say was easier? Which one's easier? Did I say which one's easier? Oh, so it must have been an afternoon class. Somebody asked me. I think U is easier. They're both going to tell you the same thing, so you might as well pick the easier. How would you have known? I didn't outright say this because I was expecting you to figure it out by looking at it, you know. Oh, they both tell you the same thing, so I could use either an H or a U. But it looks like the U is easier. I tried to give you hints that the U is going to be easier because the H you have to do what with the work? You have to flip the work, which is counterintuitive. And so, so we do the U.
We have 5 more. We have 5.
And so we're going from like say 6 moles of gas up here, and this liquid isn't going to take that much volume, but 6 times 25 is about how many liters? 6 times 25 is about 150 liters. And then the water is just milliliters. This is going to be 4 times 25, so it's going to be about 100 liters. And so we're going from bigger volume to littler volume, right? And so who's doing the work?
This was
the surrounding. And so what happens is the system gains or the system loses energy from the work done by the surrounding. It gains. This is why doing it in an internal energy diagram is easier. And so here, delta H is greater than delta U. Right? And these diagrams, have you seen them so many times that they're kind of burned in your memory, or are you going to be cramming these tonight? Then cramming, cramming, then don't give up cramming until the very last second before the exam, because you've got to keep cramming, keep cramming. A lot of people say, I met so many students who said, I'm not going to study, you either know it or you don't. And I thought, what a ridiculous way of thinking, because I don't think like that. I always think that you can learn something new in 1 second, And so you might as well just keep studying until the very last second of the test. That's my philosophy. You could disagree with that, but that's...
So, again,
if we did entropy, then we have to do the funky thing with work, which we did. We did all that. We did this all with internal energy, then we did the exact same thing with entropy. And we get the exact same answers with entropy, but it's funny how you have to do the work, so internal energy is a lot easier, I'm willing to stay as long as you guys want. So if you wanted to review some more stuff, it's okay.
So it's gain the energy, so the reduce
This is delta U here, right? So delta H is going to be greater than delta U.
final volume is smaller.
Delta H is greater than delta U.
Would we get it wrong if we use the book's definition of greater than?
If you use the book's definition, then write me a little note. I'm using the book's definition. If you state that you're going to use the book's definition, I'll tell you, the book is the situation with the general chemistry text is a lot of them do this, and so we're kind of stuck. But in practice, the book's definition is wrong, because let's say, which one is bigger, minus $10 out of your wallet or minus $20 out of your wallet? Your book would say minus $10 is bigger because it's more positive, but your wallet's going to feel a lot lighter with minus $20, right? And so energy is the exact same thing as currency. There's no negative currency, there's no negative energy. So the book is actually the way, and I'm disappointed that they did, I don't know why they did it like this. They try to make it easier, but they end up making it harder because you have to unlearn that. Eventually you're going to have to unlearn it. And so if you do the book's method, you're going to unlearn it and then learn it the correct way. When do you want to do that? But in Chem 1A, you could do it the book's way. Just write me a little note. Book's depth.
So if the final volume is bigger, so the work is like that.
Professor, for that problem,
Yeah.
Can you just do it by, actually never mind, you did it never mind.
Can you look at number 18?
Yeah. Example tab number 18.
Figure out its rating and
All right.
When you say ionization energy,
Higher, that means that the function.
Yeah, potassium has an ionization energy of 418.8 kilojoules per mole. What is the maximum wavelength of light capable of ionizing potassium?
I'm just confused, like, when this ionization interval, is that E?
It's a lot of matter.
That's an energy.
It's the word that is throwing me off. I can't tie it. So, like, ionization, light.
Ionization just means to knock the electron off.
You don't lift up.
And so, let's say if you had 410 kilojoules per mole, is that enough to knock the electron off potassium? No, if 410 kilojoules per mole of light came in, it's not going to ionize it, it's not enough. So how much energy do we need? We need,
So we have to find, so we have to find the wavelength, so we have to find.
yeah, okay, let me show you what we're dealing with here.
Oh, I think I know.
Maybe visually it might be easier to see this.
So you know this, this is what you don't know. You know Chem's concept and speak Don't put a plus? Because
So the energy is given, so we have to find the frequency, and from there we find lambda.
the energy is photon equation. E is equal to H of frequency.
So what was given to you is the energy, so you find the frequency, and then from the frequency you find the wavelength, and that's going to give you what,
So what was it?
what maximum wavelength is actually costing, right?
Well, no, I wouldn't do it like that.
Really?
Yeah. Here, this is this potassium metal, let's say. It costs you 418 kilojoules per mole. This is it. You know, this is the energy. The frequency is related to energy. I wouldn't do it that way because I do it like this. Yeah. E is equal to h mu, which is equal to hc over lambda. I just go ahead and get lambda. Rather than, you know, I wouldn't get the frequency and then convert it to lambda. I just get lambda. The trick with that question is that you have to know energy.
Yeah, so the 390 to 790.
No, not that one. You have to know total energy versus the energy of a photon. Remember we talked about that. The total energy versus the energy of the photon. How do you do that problem? We did the problem just like that in class.
One single photon is
We did the problem exactly like this. The only thing was, it was for 347 kilojoules per mole rather than 418.1. We copied the problem as we did in class, but instead erase the 347 and write 418.1 and do it exactly the same way, you get it.
I was just confused with the.
Yeah.
Dude.
Adrian, you guys have next one.
I'll tell you, it was like UV light. That one. Take a look at that problem and it's exactly the same. Yeah, I don't know, there's a class coming in. What time is the class coming in? I think we have to move to the computer lab. No, I'll stay longer.
So the one we did that, you know?
You're wrong, you need to go back here and look at it.
So I don't worry about
No, you gotta look at problems. Oh, yeah, make sure you understand it.
Yeah, it's wrong.
I don't understand that problem well enough, when we did the class.
Oh, I'm just trying to. It doesn't exact opposite. It says. Also, is that why he said? Yeah. It's definitely said you're doing your books. You have to explain it. Yeah, you have to explain it.
Because he was giving moles.
All right, we're gonna go into the computer lab.